Good afternoon, and welcome to our Wednesday afternoon press conference here at the 229th meeting of the American Astronomical Society in Grapevine, Texas. I'm Rick Fienberg. I'm the AAS press officer, and I'm assisted today by my deputy press officers, Inga Heyer in the back, who will be monitoring the webcast, and Larry Marshall, who will be manning the roving microphone. If you have a cell phone or a beeper or a pager, please silence it so it doesn't go off during the briefing. And in the next few minutes, 4 press releases will be going out in connection with each of the 4 presentations. So you can look for those in your inboxes if you're on the AAS press list, or look for them on the USRA website if you're not. I'll give a brief introduction and introduce all the panelists, then they'll give their presentations one right after the other from left to right, and then we'll take questions. If you're on the webcast and you have questions, please use the text chat box and queue up your questions for Inga. So this morning at our first briefing, we heard about some new results from a fast radio burst that was discovered at the Arecibo Observatory in Puerto Rico. All of the science that you're going to hear about today is from that same observatory. It's a 300-meter, 1,000-foot diameter, single-dish radio telescope in Puerto Rico. You'll hear more about it, I'm sure. It was a unique instrument until recently, when the Chinese inaugurated a 500-meter radio telescope of similar design. And one of the things that a lot of journalists have asked over the last 6 months is, does this mean Arecibo is obsolete? And the answer is, of course not. I mean, when you open a new telescope, all the old telescopes don't become obsolete. And so we're going to learn about some of the unique science that Arecibo has done recently, and you'll have a chance to ask some questions if you wish about where it fits in with the new Chinese telescope, which to my knowledge hasn't yet even been proven to work, though it probably does. All right, so we have 4 speakers today, all who are either based at Arecibo or use the Arecibo telescope. First will be Joan Schmelz. She's the director of Arecibo, I think. Is that right? Deputy director. I just gave her a promotion. Right. USRA stands for Universities Space Research Association, and it's an organization that very generously has helped underwrite some of the costs of operating our press office this week. Next will be Victoria Kaspi. Vicky is at McGill University in Canada. She's going to be talking about part-time pulsars. I forgot to mention Joan's topic, which is the Arecibo foreground and the cosmic microwave background. Then we'll hear from Tapasi Ghosh, also of USRA and Arecibo, who will be speaking on a venerable old radio telescope, setting a new standard for a universal constant. And finally, Chris Salter, also of USRA and Arecibo, will tell us why Arecibo Observatory radio data are crucial to understanding why quasars, the bright nuclei of active galaxies, are so very bright. So with that, I will turn it over to Joan. Your presentation will come up in just a second.
Well, thanks so much, Rick, and thanks for the promotion. I've been looking forward to that. And of course, the director is in the back of the room, so I should say I am the deputy director. And also thanks for the plug for Arecibo about how its science is not obsolete. We had a special session this morning on Arecibo results. There was a simultaneous press conference on the FRBs, which many of you may have attended. And when I first found out that these 2 were happening at the same time, I was distraught, thinking, oh, we just can't catch a break. And then I decided I wasn't going to fret about it. I was just going to embrace it, that Arecibo was just scientifically, it was the victim of its own success. So, and then we have this press conference as well. So I'm going to talk to you about Arecibo and the cosmic microwave background. And this is an all-sky image of the infant universe created by WMAP. And the small-scale structure are these temperature fluctuations that grow into the seeds of galaxies. They're the seeds that eventually become galaxies. But this image requires a lot of processing in that there are many structures in the galactic foreground, in the Milky Way galaxy, that have, in many cases, stronger intensities than these little sources here that need to be subtracted in order to get this map. Some of the well-known sources are here. These are templates for different kinds of radiation, synchrotron radiation, free emission from hot electrons, spinning dust grains, and thermal dust. And all of these different sources are frequency dependent, so these have to be subtracted from the data in order to get the map that you just saw. So there are two new results that suggest that there could be a previously unidentified foreground component that we may need to understand to show that we can measure and interpret this CMB small-scale structure. The first of these results comes from GALPHA. GALPHA is the Galactic Arecibo L-band feed array, and it's a survey of hydrogen in the Milky Way galaxy made with Arecibo. The blue at the top are the filamentary structures that are in interstellar space that are mapped by this GALPHA survey. And the yellow at the bottom is the orientation of the magnetic field from Planck observations of polarized dust. And these two taken together show that H1 filaments are aligned with the magnetic field. Now, if elementary physics leads to the first question, why is the neutral hydrogen, the hydrogen without any charge, aligned with the magnetic field? It's really only charged particles, say positively charged ions or negatively charged electrons, that would care about the magnetic field. So this is a question that didn't really have an answer. The second result comes from a series of papers by my collaborator, Gerrit Verschuur, that showed many examples of overlaps, connections, and associations of galactic hydrogen, which is seen here in color, and the CMB structure, which is in contours, including this one that's nicknamed TRIO because there are three sources. And this leads to our second question. Why is the galactic hydrogen, which is at a distance of only a few hundred light years, associated with the cosmic microwave background structure, which is supposed to be 13 billion light years away? So both of these questions can be addressed if there exists a population of cold electrons about 100 degrees Kelvin in the galaxy, in the interstellar medium. So these electrons can couple that neutral hydrogen to the magnetic field and explain our first result. And the coupling is via collisions. It can also radiate in the frequency range of 22 to 100 gigahertz, where they look for the cosmic microwave background structure. And these electrons can be associated with, but not necessarily aligned with, the galactic hydrogen. So we've used data from Planck and WMAP to plot a spectrum for one of those TRIO peaks. And this is what it looks like on the side here. But on the left-hand side of the plot, say from about 22 to 100 gigahertz, you can see that the spectrum is nearly flat, even though there are some error bars there. And on the right-hand side, above 100 gigahertz, this is the area that we know that galactic dust emission dominates. So it's not the part of the spectrum that we're trying to model. It's really the flat part that is significant for the cosmic microwave background. So our model is free emission from cold electrons, these 100 degree Kelvin electrons. But it had never really seriously been considered as a source of this foreground contamination because the spectrum is too steep. It looks something like this. And you can see that the blue line is a terrible fit to the data points. But, and this was the key to this result, what if we consider a source that's smaller than the beam? So if the source of the radiation is smaller than the telescope resolution, then you have to account for something called beam dilution. And could we model the flat data on the left-hand side with this free emission that is subject to beam dilution and make it a good fit to the data? And the answer appears to be yes. So here's the same data that I just showed you. On the right-hand side is the part of the spectrum that we don't care about because we know it's galactic emission. The straight line would be the free emission, but without beam dilution. And this line with the zigzags in it, that is when we account for beam dilution. And the zigzag is because the actual size of the beam is a factor. So at every data point, at every different frequency, there's a different beam size, and those have to be taken into account. So it turns out that this free emission with beam dilution gives you a pretty good fit to the data. The reduced chi-squared is 1.25. And if it were 1.00, if it gave you a perfect fit, you wouldn't need any cosmic microwave background. So it's good that it's not perfect. But it does seem to be significant. So just to conclude and summarize everything, we started out with these two problems, these questions about the galactic hydrogen and aspects of the hydrogen that we couldn't understand. We proposed an answer, which was this population of cold electrons. And we had a model of free emission from those electrons, but the key component was that it included beam dilution. The model fits the data quite well, but it also makes predictions. The model predicts the size and the temperature of the structures, and those can be confirmed by the GALPHA data. So for these GALPHA features, we get a temperature of about 100 degrees, and we get a source size of about 0.16 degrees. Thank you. So I think now I turn it over to Vicki.
Okay, it's a pleasure to be here today. I'm going to be telling you about part-time pulsars, and I am speaking on behalf of the P-alpha collaboration, which is a collaboration of something like 24 astronomers located around the world, but several of whom are actually here in this room today. This work is published in an astrophysical journal paper by Line et al. That I believe is coming out today. So first of all, pulsars. What are pulsars? Radio pulsars are rapidly rotating, highly magnetized neutron stars. Neutron stars are, of course, collapsed remnants of massive stars, the close cousins of black holes. By rapidly rotating, I mean rotating sometimes many times per second, sometimes hundreds of times per second, with enormous, the largest known magnetic fields in the universe. And they produce beams of light from their magnetic poles, where the magnetic... There was a problem, and Microsoft PowerPoint was closed. We apologize for the inconvenience. Okay.
Let's go back. That's interesting.
Fascinating. Maybe hit
Let's
it
try
now.
it again. See if we can bring it up.
Oh, let's hope that doesn't happen again. Okay, so they're like cosmic lighthouses because beams of light, and in most cases for neutron stars, radio waves, come out of the magnetic poles, and you see one flash of this light each time the star rotates, like a little cosmic lighthouse. These stars, because they're emitting light, they're emitting, they're giving off energy. They slow down over time very slowly, so they are born spinning very fast and slow down over time. The cartoon that you see there is an animation. Of course, it's an artist's concept. Neutron stars are only something like 20 kilometers across, so at interstellar distances, we of course can't ever see that, and all we see is the intensity as a function of time, like in the lower trace. Today, there's something like 2,500 of these radio pulsars known in the Milky Way, and they're famed. They're well known for being excellent clocks, which enable all sorts of different types of astrophysical experiments to be done, including searches for gravitational waves. And that's why astronomers like us are so interested in them. We're so interested that we want to continue to find more of these. We think we know of only a tiny fraction of the neutron stars in our galaxy. And so we've been doing, for many years now, a large-scale survey for radio pulsars in the disk of our Milky Way galaxy. As I said, this involves something like 24 astronomers from around the world. And so far, we've discovered about 175 radio pulsars, and in fact, also one fast radio burst that some of you heard about in the press conference earlier today. So this survey has been extremely productive, but it's not hard to be productive when you have the world's most sensitive radio telescope. The discovery that I'm talking to you about today is of two nicknamed part-time pulsars. These are two of those 175 discoveries, and they're notable because they're extremely unusual in that they are off for most of the time. So most pulsars, the pulsars that we know of, are generally continuously on. When you point your telescope to that same position on the sky, you see the source. But in this case, in these two cases, for pulsar J 1910 plus 0517, it's only on about 30% of the time. And pulsar J 1929 plus 1357 has been found to be on for only about 0.8% of the time. So less than 1% of the time is this pulsar actually pulsating, and the rest of the time it appears to be totally off. That second pulsar's on fraction actually abruptly changed about a year ago, and so now it's on for about 16% of the time. But for 3 years, it was only on 0.8% of the time. We know those fractions from many observations, as you could tell, of blank sky, using the Jodrell Bank Observatory. The pulsars were discovered with Arecibo and then followed up at Jodrell Bank because it required a huge amount of telescope time to be able to study them. This is a histogram, two histograms. The one on the right is for the 1910 plus 0517, and what you can see is radio intensity on the x-axis and number of observations on the y-axis, and you see the distinctly bimodal distribution of the radio intensities, where the lower peak is, as you can see, centered on 0, indicating we didn't detect that pulsar. The radio intensity was consistent with being 0 for the majority of the observations. And on the plot on the right, you can see it for 1929 plus 1357, where the even greater vast majority of the time the flux density is consistent with 0, and you can see the handful of detections of the pulsar in that tiny little peak below. What are the implications for this discovery? Well, first of all, it's clear that the radio emission mechanism, which has long been mysterious and not that well understood in radio pulsars, it can abruptly turn on and off. And even more interesting is that the spin-down rates of these pulsars depends on whether they're on or off. I mentioned earlier that all pulsars slow down with time, but the rate at which they slow down with time seems to depend on the amount of radio emission coming out. What you can see on the plot on the right for 1929 plus 1357, on the x-axis is the on fraction, which initially was about 0.8%, subsequently went up to about 16%, and the spin-down rate on the y-axis. And you can see that we've shown that the two are, given the limited data, they're correlated in that the higher the on fraction, the faster the pulsar spins down. This close relationship between slowdown forces in radio emission is kind of surprising, given that the radio emission really represents, generally speaking in pulsars, a tiny fraction of the overall energy budget of the neutron star, and yet it can affect the spin-down rate so strongly. The other implications are that there must be many more of these pulsars, just like these, in the galaxy. For an on fraction of just 1%, that means, on average, we're only going to detect one out of every 100 pulsars that's actually out there. And it's actually worse than that, because the way we do this is we detect a pulsar and then we go back and try and confirm it to make sure it's real. And if it's only on for 1% of the time, it's very hard to confirm it, even if you detected it the first time. So this implies that the known Milky Way radio pulsar population is far more incomplete than we thought. And it's difficult to estimate how many are yet unseen, since we don't know the distribution of the on fractions. There could be pulsars that have much even smaller on fractions, which would indicate that we're just detecting the tip of an iceberg. So to recap, the Arecibo telescope has discovered 2 intermittent or part-time radio pulsars. The Arecibo P-alpha survey is ongoing, and these 2 pulsars out of the roughly 175 we've discovered are highly intermittent, and this sheds new light on the radio emission mechanism for neutron stars, and also implies that there are many radio pulsars in the galaxy that are yet unseen. Thank you very much.
Good afternoon. So I'll be talking about Venerable radio telescope sets new standard for one universal constant. One of the most fundamental constants in physics, alpha, describes how charged particles interact with electromagnetic field. This is a dimensionless quantity, so it's a pure number, and it's not derived from any deeper theory. Yet it is crucial to the understanding of the nature of atomic and molecular spectra, and indeed their formation itself. For example, if its value was twice as big, atoms would decay twice as fast. So this has been a question that whether alpha is truly constant. I should mention here, alpha's value itself at the present time is very well determined in the laboratory. It's a combination of electrons charge squared divided by Planck's constant times velocity of light. So the question for studying variation of the value of alpha has been a long time pursuit. Lot of work has been put in studying quasar spectra. By that, I mean quasar provide light coming from remote past at different redshifts. Traveling to us, their light can go across gas clouds, and these gas clouds could produce absorption lines. The lines are redshifted. To identify these lines, various ratios are compared with the laboratory values. Some small departure from the present-day laboratory results are analyzed as a possible systematic effect due to variation of fundamental constants. The controversy around 2001 was that the values derived following this method from Keck telescope yielded a significant result, which implied that value of alpha was smaller about 10 billion years ago. The similar work was also done at VLT, and later it was in 2008, it was found that the second number shows that it's not very significantly changed. We can't say that the value of alpha was lower or different to their current values. So here we present an Arecibo result. These, we have been following a radio quasar that happened to be sitting at the background, in front of this radio quasar. There is a hydroxyl molecular cloud. It's part of the host galaxy that's hosting the quasar, basically. And it's at a redshift of 0.245. And so when the light radio emission passes through this OH molecular cloud, the cloud produces absorption lines, or it could also excite emission by Maser mechanism. So the spectra of OH is very well understood in the laboratory measurement. For this particular source, it so happens the transitions are such adjusted that one of the lines that's supposed to emit at 1612 megahertz is seen in absorption, while the line at 1720 megahertz is seen in emission. So these two lines are called conjugate. They are basically mirror image of each other. So if you took the two spectra, one in emission and in the absorption, their velocity structure, their profile look so similar that if you simply add them, they basically, we don't see any shift, any change, any residual in this, in the added spectrum. So if value of alpha was different from their modern values, from their current values, then we would have seen a shift between the emission and the absorption line in this case, which can be accurately calculated. Now, we have observed this particular source for 125 hours. The spectrum you're seeing here is probably the deepest radio spectrum taken towards any single radio source. And we see no shift between the emission and the absorption line. So this implies that value of alpha has not changed, and we could put this most stringent constraint on it, which is it hasn't changed by 1.3 parts in a million in the last 3 billion years. So more accurate results reaching farther back in time would require finding more distant quasars that are also obscured by OH or other well-studied molecular clouds. There are various searches going on at the moment to find relevant sources. Here, I should also mention that Webb et al. In 2011 and later in 2012 apparently have claimed that there is a spatial variation of the value of alpha. All these spatial or temporal variation of alpha has deep significance, that various theories that try to unify standard model of particle physics and gravitation, various higher dimensional models actually predict that alpha might change with space and time. But so these are the questions that need to be verified. So I'll leave it here. Thank you.
Excellent. Thank you very much. Like a good, dutiful husband, I follow 5 steps behind my wife. I'm going to talk about Arecibo observations taken together with the RadioAstron orbiting Russian satellite. You see Arecibo on the left and at RadioAstron on the right, and a typical picture of what we think an active galactic nucleus looks like, sat in the middle, which both telescopes would be observing at the same time and combining their signals to get an extremely high resolution set of data on the object. First, I thought I'd just mention what the RadioAstron orbital telescope's orbit looked like. It's an extremely elliptical orbit. It's only 600 kilometers above the Earth at its nearest point, its perigee, and it goes out to 330,000 kilometers, which is very close to the distance of the Moon. It's a heck of a long way out there. It takes about 8 days to complete one orbit. And it means that the size structure that one can see with an Earth telescope combined with RadioAstron changes as RadioAstron goes about its orbit. You might wonder why we mentioned the importance of Arecibo for this. Well, Arecibo is the single most sensitive centimeter wavelength radio telescope on the planet. And RadioAstron is only a 10-meter dish sitting out there in space. So to observe a large number of active galactic nuclei, it needs to work with the biggest telescope available, the most sensitive telescope available on Earth, and that is Arecibo. Another digression, I thought I'd mention something called the Compton Catastrophe. Radio interferometry measures, in practice, the brightness temperature of a compact radio source. The longer the baseline, the higher the brightness temperature that can be measured. Space VLBI provides the longest possible baselines between the two telescopes forming the interferometer, and consequently, it's able to measure the highest available brightness temperatures if they exist. And that's one of the reasons that RadioAstron was built and sent up into space to investigate. Now, the relativistic electrons in a radio source core could, in theory, reach energies that would take their temperatures up as high as one wants to. But in practice, once they get above about 10 to the 11 to 10 to the 12 degrees Kelvin, 10 to the 12, of course, being a trillion degrees Kelvin, they are cooled by something known as Compton scattering, where the radio photons generated are scattered by the high-energy electrons that are radiating, and they're scattered up to X-ray or gamma-ray energies. And this takes energy from the relativistic electrons that are hence cooled. And for the electrons, this is known as the Compton Catastrophe. If electrons have effective temperatures greater than, say, 10 to the 11.5, then they'll be cooled down to that temperature in less than a day by the Compton Catastrophe, and that will represent the maximum temperature for the relativistic electrons in the active galactic nucleus. Well, finally, round to some results. This is the graph of the brightness temperature, runs from 10 to the 11 up to 10 to the 14 and a little bit higher, 10 to the 14 being 100 trillion degrees Kelvin. The number of detections run up the y-axis, and as you can see, typical is a little bit above 10 to the 13, 10 trillion, and the hottest temperature we've seen is above 100 trillion. We'll come back to that in a moment. I thought I'd give a case study, which is the quasar 3C273. It was the first quasar identified, I guess, getting on for 45 years or so ago. 3C273 is located at the center of a giant elliptical galaxy, and the picture on the left you see to the right of the slide is an optical color picture of 3C273. You can see the burned out, saturated quasar on the left, which is saturated both by the quasar light and light from the host elliptical galaxy. And there is, in fact, an optical jet seen being blown out of the quasar, running to the lower right. On the right is a radio picture, actually made in this case by the Merlin radio telescope in the UK. And the quasar, here we don't see the elliptical galaxy. You can see the quasar where the jet is emanating from, and the details of the jet, which won't further interest us today, out to the bottom right. 3C273 is one of the closest quasars, and it's thought to contain a central massive black hole containing about 1 billion solar masses. And this is believed to be the object that is the engine for the jet that is coming out of us, out of the AGN, and which generates the radio emission that we see. With RadioAstron and Arecibo, we're actually looking very close to the central black hole itself. If you look at the rightmost picture, it's the small red dot at the top of the jet on the left-hand side of the picture. Its jet, incidentally, is about 200,000 light years long, but we are looking right at the central light month, I guess, of the jet itself. And the temperature that RadioAstron and Arecibo reveal for this object, the highest yet recorded is about 42 trillion degrees Kelvin in brightness temperature, way above the maximum of 1 trillion degrees that synchrotron generation of radio waves predicts. So what do these high brightness temperatures imply? As I said, they're up to 100 times the predicted limit for relativistic electrons radiating by synchrotron emission. We certainly know that as jets have speeds going close to the speed of light, they boost the intensity and hence the apparent brightness temperature of the object we see. But we can measure the velocity of the jet in 3C273, for example, and it does not provide enough Doppler boosting to reach the brightness temperature of 40 trillion degrees that we see. Other scenarios have been suggested, like synchrotron emitting protons, or maybe so-called coherent emission, where the electrons all join together to emit in phase, but these are also probably ruled out by brightness temperatures of 100 trillion degrees. What's the future? Well, RadioAstron Arecibo observations continue. You'll see both Tapasi and I have tired-looking eyes, and that's because we spend so many nights at the telescope helping run the interferometric observations with RadioAstron. To date, the highest measured brightness temperature is indeed about 100 trillion degrees Kelvin. However, in theory, at its furthest from the Earth, RadioAstron to ground telescopes could measure 1,000 trillion, or maybe even a little bit more. The big question is, as we carry on observing, will they be? Because every time the maximum temperature goes up, the explanation of the mystery of the high temperatures becomes a little bit more. Thank you very much.
Just leave it. Thank you. All right, thank you very much for those presentations. We will go to questions and answers now. If you're on the webcast, please queue up your questions for Inga. If you're here in the room, please raise your hand, and when I call on you, identify yourself and indicate who you are addressing your question to, and make sure you wait for the microphone from Larry. All right, let's start here in the room. Questions? Don't be shy. You're going to force me to start asking questions. Okay, go ahead, Martin, down here.
I'll ask a quick one. Martin Ratcliffe, freelance for Joan. So what are you saying as far as the impact on the recorded CMB that we have that you think might be contributed by these weird signals that you're finding?
So,
What's the implication?
I would claim that the signals that we're seeing are probably much less weird than the CMB, and that you can look at it as a component of the Milky Way that we might not have known was a source of foreground emission. So just like the cosmologists knew to subtract synchrotron radiation and thermal dust and spinning dust, this is a component that they might not known of to subtract, only because we really didn't know it was there. It's difficult to detect, right? So you have to build billion-dollar satellites in order to detect it. And I suspect that they never would have built the billion-dollar satellite if they thought they were studying the Milky Way galaxy. They thought that they were studying cosmic microwave background. But I think this is another source of emission that they have to account for in order to understand even better the cosmic microwave background structures.
I'm going to take the chair's prerogative to ask a follow-up because I had a question related to what Martin asked, which is, it sounds like you would need to do more modeling before you could hazard a guess at what the CMB map would look like if you were to subtract the electrons, right? The cold electrons. What do you need to do to collect enough information about this possible other source to be able to sort of do a rough draft of subtracting it from the CMB? And do you have any anticipation of what that might do to change the characteristics of the CMB that Planck and WMAP measured?
So I showed you one line of sight, right? So of course, across the whole sky, there are many, many more lines of sight than just one. So the data are available. Anyone can take a look at it, and they're all public domain. And using this method or model with the published beam sizes gives you could make a map. So anyone could make a map. So it would, for me or for my collaborator, Garrett for sure, I think it might take a lot. I know that we're going to continue to work on it, but one line of sight at a time is probably a bit slow, and maybe we need the cosmologist. It would be absolutely wonderful if the cosmologist became interested enough in this possible source of foreground emission to be able to refine their result with the resources that they have.
Okay. Right, I thought there was another question.
I think that was the collaborator in the audience.
I think there was another question over here. No? Inge, do you have any questions online? Okay, let's go to the webcast then.
We have a question for Dr. Kaspi from Irene Klotz of Discovery News and Reuters.
Yep.
So what are the current theories about why a radio pulsar may be intermittent?
Right. So there could be a variety of different reasons. There could be low-level magnetic changes. We know that the radio emission must be intimately connected with the magnetic field. And if the magnetic field has structural changes, and we see evidence for those kind of structural changes in some neutron stars, more typically in very high magnetic field neutron stars that we refer to as magnetars. And in those cases, we see large changes in radio emission, and in fact, those are extremely intermittent radio pulsars. So that's one possibility if the magnetic field is a little unstable or undergoes some sort of physical changes. I think that's the most likely. It has to be something in the magnetosphere. It has to be something on the outside. So it must be related to instabilities in that. I think that's the most likely. I mean, there's other possibilities. For example, if the actual structure, the physical structure of the crust of the neutron star undergoes changes, little crust cracking. That can affect the neutron star. That can result in some charged particles being introduced into the magnetosphere, which could affect the radiation that we see. That's another possibility. But I think most likely it must have to do with the structure of the magnetosphere and the structure of the magnetic field.
Thank you.
Anything else from the webcast? Any other questions in here?
Yes.
Go ahead, Larry.
Larry Marshall, Deputy Press Officer. I'm not quite clear how this intermittence appears to you. Are we seeing losses of syllables, whole words, or are there periods where it doesn't communicate with us at all and then it turns on again?
So in the case of the pulsars that I was presenting, it's the third of your three options that it seems to shut off entirely and then turns back on at a fairly high level. These pulsars are not, when they're on, they're not particularly dim. You wouldn't know that they have this sort of dual personality. But I think the question that you're asking raises a very interesting, more general point, is that we know of lots of neutron stars that exhibit intermittent radio emission on different timescales. There's a whole class of really pulsars, neutron stars, that we refer to as fondly as RATs, rotating radio transients, that seem to emit short bursts, 1 or 2 pulses, just 1 rotation's worth of radio emission, and then are silent most of the time. But those will produce maybe once per hour, maybe once every few hours, a single pulse. Whereas these sources, so this is sort of a new phenomenon where when they're on, you see pulse after pulse. You'll see it for 20 minutes. It'll be totally on, every pulse is there. And then it'll shut off for weeks or months, and you see absolutely nothing. So there's this whole spectrum of radio phenomenology going on in these neutron stars. Very, very curious, very interesting.
Yes, I remember one a few years ago where we were actually seeing precession. Actually, the beam was going in and out of alignment with the Earth over time. But that was a different...
Well, you might be referring to some of the relativistic binary pulsars where general relativistic effects cause the beam to come in and out. Now that's different. That's a different thing.
That's a different thing.
That's really a geometric thing, whereas here we think the emission mechanism really is turning on and off.
I have a question for you too, Vicki. This morning we heard about the fast radio bursts that are erratic, or a fast radio burst that's erratic, and the panel of presenters was not unanimous or perhaps not enthusiastic, but they nevertheless seemed to feel that if they had to bet, maybe they'd bet on something involving neutron stars. But they're also talking about a source that's billions of light years away in another galaxy. Now, all the pulsars that you're describing are in our own galaxy, correct?
Yes. Or there's a few known in the Magellanic Clouds. But
okay, but they're all nearby, relatively nearby. Based on the intensities, maybe you can rule out any kind of potential connection between fast radio bursts and these intermittent pulsars. But it just seems to me like we're talking about, relatives of the same kind of phenomenon, basically. I'm just wondering if you have any thoughts on whether we might be seeing the equivalent of a fast radio burst type object that just happens to be nearby, or whether you really think it's apples and oranges.
I think that's a great question. So the thing that's important to recognize is the vast difference in energy scale. So because the repeating fast radio burst is so very far away in a redshift of 0.2, the amount of energy each burst contains is many, many orders of magnitude greater than any of the pulsars we've seen in our galaxy. Now, that doesn't necessarily rule out a connection. Mainly, and it comes back to a point that was in the presentation, that the radio emission in neutron stars typically represents a tiny fraction of the overall energy budget. And particularly for the most energetic of radio pulsars, for example, the Crab pulsar, there is at least a little, maybe a super Crab, there is in principle enough energy in the neutron star to power a fast radio burst and the repeating fast radio burst. So it's not totally.
It's
I don't
just a
think
lot
the
of that
dual-
energy is coming out at other wavelengths, but you're saying if it were channeled into radio, it could be that bright.
That's
Yeah.
yes.
Yeah. Okay. And I have a question for Chris Salter as well. When you were describing brightness temperatures of hundreds of trillions of degrees potentially, I mean, what is the relationship between that temperature and anything physically going on at the source? I mean, are we talking about a theoretical construct here, or are we talking about some physical process or object that's actually at a temperature of trillions of degrees?
The temperature, of course, represents an energy, and it's describing the energy of the electrons in terms of temperatures. In terms of radio astronomy, the effect would be if you could take the quasar away and replace it with a hot body. That would be the temperature of the hot body of the same size as the quasar would have to have in order to emit the same amount of emission. So it's an equivalence, but it's equating energy and temperature together.
Okay. No one wants to hypothesize that somebody's plugging and unplugging the Arecibo telescope every now and then just to play with you? Okay, we have a question over here from Ethan.
Hi, Ethan Siegel from Starts with a Bang. This question is about time-varying alpha or spatially varying alpha. It's wonderful that you've been able to go so far. I'm sure Dr. Webb will be very disappointed in these results. I'm very curious if you saw any sort of variations depending on the orientation you were looking at in the sky, because that was Webb's major claim, is not just at distant redshifts, but at different galactic coordinates, you were seeing slightly positive, slightly negative result. If you separate your results out by that, have you seen any indications, even at the 10⁻⁶ level, that might indicate a variation in alpha?
To do that, we need radio quasar in different direction of the sky and with an appropriate cloud doing the similar kind of perfectly matching emission and absorption. So this object in a way is unique. There are just 2 objects in the sky that I know of that produces this kind of matching emission absorption line. So unfortunately, we can't do this spatial distribution test. If we are looking for radio objects with this absorption line in different parts of the sky, if we have that much of information, we would be able to comment on it. So Dr. Webb's result is absolutely fascinating, and it is absolutely wonderful work that they have done over the lot of many years. He has surveyed many quasars in different directions of the sky, so he can comment on this. Our result only can address his time variation, not his spatial directional variation.
Any other questions come in online? Okay, anything else in here? Well, we've nearly used up the hour anyway, so it sounds like a good time to stop. I want to thank you all for your presentations. I want to also give a shout out to Soraya Faruqi in the back from USRA for helping to organize this briefing. Our next briefing will be tomorrow morning at 10:15 Central Time, and the topic will be galaxies and black holes therein. So we'll finally be switching a little bit away from radio astronomy and talking about some other things. I think that's it. Just be on the lookout for those 4 press releases coming from USRA this afternoon. Thanks a lot.